In this video, we're going to take a brief look at what an elementary matrix is, and then some of the basic properties of an elementary matrix. And then in a subsequent video, we will take a look at how elementary matrices are related to the inverse of an invertible matrix. Right? So what makes a matrix elementary? So a matrix is elementary if it is formed, by applying a single row operation to our n by n identity matrix, right? So if you perform one row operation on the identity matrix, what you will get is an example of an elementary matrix, right? And the key is it's exactly one operation that you're allowed to perform. So just to illustrate this, let's look at a couple examples. Suppose I start with I3, or 3 by 3 identity. Right? The 3 by 3 identity, it's not too big, but it's just big enough that you'll see certain patterns. If I perform, say, 4 times row 2 added to row 3, right? So we know row 1 will stay the same. Okay. Row 2 will stay the same. And then row 3 will become 0, 4, 1, right? And then this is an example, so this matrix is elementary, right? And what's also interesting as well, you can tell that it's close to the identity, but you have a single non-zero entry that's either below, or it could have been above, depending on what row I chose to add to. Right? But the interesting thing is, look at the position of this entry. This entry is in row 3, column 2, and it's not a coincidence, right, that this entry here is the 2, 3 entry, and it's actually the 3, 2, not the 2, 3. So this is the 3, 2 entry, and it comes from that 2 and that 3. Right. So in general, if you have something like an identity matrix and you have a single entry that's either below or above the main diagonal, the position of that entry will tell you exactly what row operation was performed. Right? In fact, it's going to be your times row add. What if we start with I4, right? So what if we took the 4 by 4 identity, right? And let's do something simple. Let's say we do a row swap. So if I swap row 1 and row 3, let's see if we can observe any kind of pattern about this operation used to perform, again, an elementary matrix. So row 3 is now going to be up here, so we'll have the 0, 0, 1, 0, and then we have that, and then row 1 is now going to be here, and then of course row 4 stays the same. Right? So how can you tell and look at this one? Well, if you notice, we don't have the 1s on the main diagonal anymore, right? So, the 1 that was here is now down here, the 1 that was here is now up here. So when you look at a matrix where you have exactly a single pair of zeros on the main diagonal and everything else is 1, and then you look at where those new positions are, So the one that was here is now in uh, this position 3 1, and then the one that was here is now in the position 1 3. So basically, you look at these two numbers, and now we have ones in the position 1 3 and ones and a 1 in the position 3 1, but we don't have ones in the 1 1 or the 3 3 position, right? So basically, it's a little hard to describe, but what do we observe in this case, right? So we don't have ones in the 1 1 position and the 3 3 positions, right? So those are the things that are glaringly obvious, but we do have ones in the 1 3 and the 3 1. So I'll just say, and so 1 3 and 3 1 has ones, right? And that's an indicator that what was used to perform or to create this elementary matrix is a row swap, right? And same thing would have happened if we'd swapped like row 2 and row 4. We would have zeros in the 2 2 and the 4 4 position, but then we would end up with ones in the 2 4 and well, this is the 4 2 position, and then the 2 4 position here, right? So it's a little cumbersome to try to write it down, which is why I'm just illustrating these facts with that examples, right? And then the last one, obviously, let's say we took I5, right? So let's keep upping the dimension here. So if we take I5, right, so that's I5. Well, almost. Here we go. Here's I5. And then obviously the last row operation that we can do is simply multiplying by a constant. So if I take like negative 3/5 times row 2, well, here is a resulting elementary matrix. So the only row that will change is row 2. And what I will end up having now is this constant in the 2 2 position. So we'll have the negative 3/5, and then everything else stays the same. Right? Again, these are probably the easiest ones to recognize. So what we're missing is, again, we don't have ones on the main diagonal, but what we have is a diagonal matrix where exactly one position is not a 1. All the other positions contain a 1, but then you have that particular entry that's not 1, and it's not 0 either, right? So the diagonal is entirely non-zero, but not filled with 1s. And then it's easy to recognize which of the operations are used, right? So these are elementary matrices. We typically denote them with the letter E, E for elementary. Now, what's interesting about elementary matrices is that they're always invertible, right? So for instance, let me use I2. So I'm just going to use the I2, the 2 by 2 identity to illustrate this, right? And here is an interesting fact. Every elementary matrix is invertible. Well, why is that? Well, think about the process that we have for finding the inverse of a matrix. It's the ability to take the square matrix and convert it, right, using our row operations into the identity matrix. So if elementary matrices are one operation removed from being the identity, then they have to be invertible, right? So every elementary matrix is invertible. And it's actually very easy to write down the inverses if you think in terms of the operations, right? So let's say, I'm going to write down, so let's say I have E1 here, and I'll do one of each type. So E1 looks like this, right? And what I'll write down here at the bottom is the operation that would be used to perform or to create this matrix. Well, in order to get a 5 in that position, I would have used 5 row 1, right? Applied to I2. Right? And then it would create this elementary matrix that I see right here. But let's see if we can just write down what its inverse would be. E1 inverse, well, that would be the operation that would take E1 and turn it into the identity matrix. So I would have to undo this operation. Well, if I want to go back and get a 1 here, I would have to take the reciprocal of this constant. So the inverse of this elementary matrix is another elementary matrix, but instead of having the 5 in that position, I'll have 1/5 in that position, and this is what it would look like, right? Right? So these two, let's say if you were to multiply them, you will get the identity, right? And I encourage you to try that. But the key here is that being given one elementary matrix, it's very easy to write down its inverse. We don't have to do the formal process. I mean, we could, but just think in terms of undoing the row operation that was used to create it, and then that will give you the identity. So the operation here for this one would be 1/5 R1, again applied to I2, right? So essentially these two elementary matrices, if we were to multiply them, would essentially nullify each other, and we would be right back at the start. And that's the definition of a matrix and its inverse, right? The product will give you the identity, right? Let's use another type of operation. Let's again illustrate all three. So let's say we do now with using the 2 by 2 matrix for a row swap, then we really don't have much of a choice because we only have 2 rows to work with, right? So obviously in this case, the operation here is row 1 swapped with row 2, and again it will be performed on I2, and that's how this one would be created. Well, if I wanted to undo this, well, I just swap them back. So I perform the same operation, which is really interesting. So if I wanted to find the inverse of this elementary matrix, yeah, perform the same row swap. Put the 1 back up there and put that 1 back down there. So the operation would be, let me write it again, it would be the same, right? And again, applied to I2, and I would get. So basically what happens, what's really interesting is when you look at these, here's an example of a matrix where its inverse is itself. Because if I multiply these two, right, I will get the identity matrix. Just to show you quickly. Like if I took this row and multiplied that column, right, I would have 0 and then plus 1. So I'll have a 1 in the first row, first column. And then for row 2 times column 2, I'm sorry, row 1 times column 2, I'll have a 0 plus a 0. Similarly, row 2 times column 1, that will give me 0 plus 0. So again, I'll have the zeros on the off diagonal. And then finally, if I took row 2 times column 2, I'll have 1 plus 0, right? So again, what's really interesting, the inverse of a row swap, right, is the same row swap. You do it once, right, you move away from the identity, and if you do it twice, then you'll go back to the identity, right? And then quite likely we would expect this pattern to continue. What pattern am I referring to? But if you notice, the pattern is if I do a times row, I will do another times row to undo it. If I swap 2 rows, I will do the same row swap to undo it. Let's say I do, again, one of the more not really complicated, but the ones that we use to eliminate a lot of entries. So let's say I take this, I take my 2 by 2 identity matrix and I perform this operation. Let's say I do 2 times row 2 added to row 1. Well, what that would mean, let's think about it. I would have to have a 2 in the 1, 2 position, right? So I'd have to have a 1, so the 1 is still there, but then I'll have to have a 2 there, and then 0 and 1. Okay? So I performed this operation on I2 to create this elementary matrix. Now, what would be its inverse? Well, what I would need to do is to go from this back to the identity matrix. I would have to eliminate this 2 by taking negative 2 times row 2 added to row 1. So added to this, right? So that means the inverse of this type of elementary matrix is going to be another one of a similar type. But instead of having a positive 2 there, I'll have to have a negative 2, right? Because the operation that will be used to essentially nullify this would have to wipe out that positive 2. Well, how do I do it? I would have to take negative 2 times row 2 and add it to row 1. That will take me back to the identity, right? So this operation here would be this one, right? So what this set of examples are meant to illustrate is that all elementary matrices are invertible, right? And to figure out the inverse, you just have to figure out what operation would undo the row operation that was used to create that elementary matrix to begin with. All right? All right. So here's our last important fact about elementary matrices, and it's what effect they have on other matrices. So let's continue to use these examples, the E1, E2, E3. So I'm going to take, so let A be just a generic 2 by 2 matrix, right? And let's see what happens if I take my E1, which defined above was 5, 0, 0, 1. What if I took this matrix and then multiply A? And let's see what happens, right? So if I take E1 times my general 2 by 2 matrix, this is the setup, and then we have to do our matrix multiplication, so we have to do the dot product of rows and with columns. So now starting with the first row, I'll have 5A plus 0, so 5A plus 0. First row, second column, that will give me 5B plus 0. Second row, first column, that's 0 plus C. And then finally, second row, second column, 0 plus D. So when I simplify this, I get 5A, 5B, C, D, right? And look at the pattern. Remember what operation was used to produce this elementary matrix. I took the identity matrix and I multiplied the first row by 5. And look at what that elementary matrix now does to our general 2 by 2 matrix. It does the same thing. It takes that general 2 by 2 matrix and multiplies its first row by 5. Right? What if we do the row swap one? So remember E2 was where we swapped, well, again, we didn't have much of a choice, but row 1 and row 2. So let's take E2 and multiply, again, my generic, run-of-the-mill 2 by 2 matrix. Oh, let's write down my E matrix first, so like that, and then times A, B, C, D. Well, let's see what happens when I do my matrix multiplication. Again, row times column. So I'll have 0 plus C, 0 plus D, and then A plus 0, and then B plus 0. So look at what we're left with. We now have, it's still a 2 by 2 matrix. That's expected. So we have C, D, A, B. So multiplying, again, my matrix A by this elementary matrix, it performs the same operation that was used to create it. Because this was created by doing a row swap, and now if I take any 2 by 2 matrix and do my pre-multiplication using this elementary matrix, it results in a 2 by 2 matrix where the rows are swapped. Notice the first row here is AB, and now the second row is AB. Second row here at the start before the multiplication is CD. After the multiplication, that CD is now your first row, right? So hopefully you're seeing the pattern. And let's finish it out with our E3. Now E3 was the, let's see, it was 1, 2, 0, 1. And this was when I took 2 times row 2 and added it to row 1 of the identity, and I created this elementary matrix. So now let's see, is it going to do the same? So let's take this elementary matrix, multiply my generic 2 by 2 matrix. Well, generic is probably not a good name, but more arbitrary. So it could be any, right? Well, let's do our matrix multiplication. So again, row times column. So 1 times A plus 2 times C. So that's A plus 2C. And then first row, second column, so B plus 2D, right? So there's our new first row. And then the second row is 0 plus C, and then 0 plus D, right? So if we write this down in our simplified form, what do we end up with? A plus 2C, B plus 2D, and then C, D. So look at what happens. So this was the matrix that we started with. And if you look at the end result, it looks like we've taken 2 times the second row. That's where the 2C and the 2D comes in. And then that is added to the first row with no change to the second, right? So that's exactly what how this elementary matrix was created. We took 2 times the second row and then added it to the first row in our identity matrix. So the other important fact that we need to make note of is this, right? If E is an elementary matrix, right? And A is any n by n matrix, right? So if A is any n by n matrix, then pre-multiplying, right? So pre-multiplying A by E, in other words, doing this, EA, performs the operation used to create E on A. So whatever operation we use to create this elementary matrix, whenever I do pre-multiplication using E on any corresponding n by n matrix, it's going to perform that exact operation on A. So if we swapped rows 5 and 21 to create E, then multiplying by E will swap rows 5 and 21 in A. If E was created by taking row 70 and multiplying by 1/2, then when I do this multiplication, it's going to take row 70 of matrix A and multiply by the same constant 1/2. If E was created by saying 5 times row 7 added to row 12, then multiplying by E will do 5 times row 7 of A added to row 12 of A, right? So basically what this gives us is it now gives us a way of representing the elementary row operations using matrix multiplication, right? So basically now we've used row operations many times, right? So row operations are now equivalent to matrix multiplication, but not just any old matrix multiplication. Matrix multiplication using elementary matrices. Right? So using elementary matrices. All right. So that's our brief look or brief intro to elementary matrices, and in the next video we're going to see how these fascinating matrices are related to the inverse, and that essentially will bring us full circle. Right? See you then.